All right, today we're pulling back the curtain on the internet's universal language. We're talking about the invisible set of rules that lets literally billions of devices chat with each other every single second. So let's just dive right in.
Seriously, think about that for a second. You hit send on an email, and that super simple action kicks off this incredible journey. Your data has to navigate a massively chaotic global network to find one single destination among billions of others. How on earth does it do that? How do we get perfect order from all that chaos?
Well, to figure that out, here's the roadmap for today. First, we'll look at the core problem the internet had to solve. Then we'll unpack its layered rulebook, see how every device gets its own unique address, compare different delivery services, and finally, see how it all comes together in the apps you use every day. So first up, the fundamental challenge. I want you to imagine trying to build a global postal service, but every single city uses a different language, different envelope sizes, and totally different address formats. I mean, it would be a complete disaster, right? Well, that was the early internet. You had all these different computers from different companies, and they're all speaking their own private languages. For a truly global network to even exist, they all had to agree on one universal language.
And the solution is this brilliant thing called the TCP/IP protocol suite. You can just think of it as the internet's official rulebook, or its universal postal regulations. It's basically a whole family of rules or protocols that every single device agrees to follow. And that's what ensures a message you send from your phone in Tokyo can be perfectly understood by a server in Toronto.
Now here's what's really clever. This rulebook isn't just one giant messy document. No way! To keep things organized and manageable, it's broken down into distinct layers, and each layer has a very specific job to do. Kind of like different departments in that postal service we were just talking about.
The original blueprint, this conceptual thing called the OSI model, actually had 7 layers. A little complicated. But the internet we actually use runs on a much simpler 5-layer version called TCP/IP. Think of it like a digital assembly line. Each layer does its own specific job, then just hands the data off to the next layer in line, starting from your app and going all the way down to the physical wires and radio waves that carry the actual signal.
So, let's zoom in on one of those layers, layer 3, the internet layer. This is where the real magic of addressing happens, and it's all thanks to the Internet Protocol, or IP. This is how every single piece of data gets its own unique digital mailing address.
At this layer, your data gets chopped up and put into these little packages called IP datagrams. And the best way to think of a datagram is as a digital envelope. It has 2 main parts: the data itself, that's the letter inside, and a header, which has all the crucial addressing info on the outside. And just like real-world shipping boxes, these digital envelopes have a strict size limit. A single IP datagram can hold, at most, 65,536 bytes of information. If your message is bigger than that, no problem. It just gets split up across multiple envelopes. Now that header is absolutely critical for delivery. It's got the source and destination IP addresses, of course, but it also has this really cool thing called a time to live, which is basically an expiration date to stop lost packets from just circling the internet forever. It also tells the network what's inside. Are we dealing with a reliable TCP package or a super fast UDP postcard?
And the network follows these rules with like zero tolerance. For example, if a device gets a packet that starts with these specific bits, it's instantly discarded. Gone. So why? Well, the first 4 bits, 0100, correctly identify the IP version. That's fine. But the next 4 bits, 0010, specify the header length, and that translates to a length of only 8 bytes. That's way below the required minimum of 20 bytes. So the system knows the packet is corrupt, and it just throws it out.
But here's a little wrinkle. An IP address is kind of like a street address. To make that final delivery to the right digital doorstep on a local network, a computer needs a specific physical address. So, to find it, a protocol called ARP basically just shouts out a question to everybody else on the local network. And this is how ARP just brilliantly completes the puzzle. The computer that has the matching IP address hears that call and replies directly, saying, "Hey, that's me, and here's my unique physical hardware address." And boom! Now the data can be delivered to the exact right machine. It's so simple and so effective. Okay, so our packet is addressed correctly, but now we have a choice to make. What kind of delivery service do we need? Do we need something super reliable and guaranteed, or something fast and efficient? That choice gets made at the next level up, the transport layer. And here, we've got 2 main options. First, there's TCP. Think of this like sending certified mail.
It establishes a connection, it guarantees every single packet arrives, and it makes sure they're all put back together in the right order. This is perfect for things like email or loading a web page. Then you've got UDP, which is more like a postcard. You just write it and send it. It's way faster, but offers zero guarantee of delivery. This is what you want for video streaming or online gaming, where a little bit of data loss is fine, but speed is everything.
So how does TCP pull off that certified mail level of reliability? Well, it uses this really clever system of acknowledgements. It's like a conversation. First, the sender sends a packet, which is numbered in a sequence. The receiver gets it and immediately sends back a tiny message, an acknowledgement. It basically says, "Roger that. I got packet 1, go ahead and send the next one." And only after it gets that confirmation does the sender transmit packet number 2. This constant back and forth ensures that absolutely no data gets lost in transit. If an acknowledgement doesn't show up for some reason, the sender just resends the packet it's waiting on. Simple as that. Okay, we finally made it to the top of the stack, the application layer. This is where we find all the protocols that our apps actually use. They're the ones that determine the content and the format of the letters that we're sending in all those digital envelopes.
And this is where we see the whole thing come together. So when you type a web address into your browser, DNS acts like the internet's giant phone book to find the right IP number. Your browser then chooses TCP for a reliable delivery. That request gets packaged into an IP envelope and sent out. And the server on the other end uses a protocol like HTTP to format the web page data and send it all the way back to you, following the exact same set of rules. It's this beautiful, layered dance.
Now you can see this entire system is built on having enough addresses for everyone. The original version, IPv4, has pretty much run out of them, but its replacement, IPv6, provides a number of new addresses that is it's almost impossible to comprehend. As Simpson-Garfinkel calculated, it's enough for 5,000 addresses on every single square micrometer of the planet's surface. Just wow.
And that kind of leaves us with a final big thought. These fundamental rules of communication, TCP and IP, they were designed to connect computers. But as we start connecting everything else to the network, your car, your fridge, your coffee maker, what does that mean for our world? These protocols won't just define the internet anymore. In a very real way, they're going to define our reality.